Hey, it's Dr. J. Part 2 of the trigonometric identities today. Today we're going to talk about even and odd functions and proving identities. All right, so let's get started. We'll talk about the even and odd functions first. What does it mean to be even or odd? Let's go ahead and recall the definition. A function f is called even if and only if f of x is equal to f of negative x. That's what it means to be an even function. Essentially means that the graph is symmetric about the y-axis. So you have, a point here, x, and then you have the y value, f of x. And then on the other side of the graph, you have negative x. I don't know if you can see that. Let's see, x, negative x. And it has the same y value. So f of x and f of negative x are the same y value. So that's the definition of even. And the definition of odd. So definitions, there are two of them. A function f is odd if and only if f of negative x is equal to negative f of x. So very similar type of diagram here. But the graph would have to pass through the origin in order for this to be true. And you would have x and f of x. So this is the value of f of x. And then over here, you have negative x. And the y value is negative. Well, it's f of negative x, sorry. F of negative x. So there's different kinds of symmetry. An even function is symmetric about the y-axis. And an odd function is symmetric about the origin. So the symmetry f of x is equal to negative f of negative x. Or in other words, f of negative x is the opposite of f of x. So these are your two types of functions, even and odd. You can kind of tell by what I'm getting at here. These are trig functions typically. I just drew a small little piece of it, but this one is cosine. And this one was supposed to be sine. So for example, sine x is odd, and cosine x is even. So let's go ahead and start with that. Cosine x is an even function. Sine x is an odd function. So what do we mean by that? We mean that cosine of x is always equal to cosine of negative x. Yeah. But sine of x Sine of x is odd. So we say negative sine of x is equal to sine of negative x. So these are your evens and odds for sine and cosine. Sometimes we reverse the order. Sometimes we also write it this way. It really doesn't matter which way you write it. All right. We also can use other arguments. So you could use t. You could use theta. Maybe alpha or beta. And the list goes on and on and on and on and on. There are lots of different arguments that you can use for a function. You can even plug in a specific angle. Yeah. You could plug in a specific angle. So cosine of negative pi over 3 would be the same as cosine of pi over 3. Easy to see that on the unit circle. Pi over 3 is 60 degrees. If you're using degree measurement, that would be 60 degrees. That would be your angle. 60 degrees, or the arc length from 1, 0 to the point cosine t, sine t. So the x value here would be 1/2. Yeah. And so what does a negative pi over 3 look like? So this would be cosine of pi over 3 here. For negative pi over 3, negative pi over 3 would just go the other direction. So remember, a negative angle just goes clockwise. I know that takes a little getting used to. Negative is clockwise. Positive is counterclockwise. So you would have the same triangle down here. This would be cosine of negative pi over 3, which is also 1/2. See, the x value here is still 1/2. Remember, this is a unit circle, so the hypotenuse is 1. If you want to blow this up, it would look like a triangle like this. 60 degrees, this side is 1/2, this side is 1, and this side is square root of 3 over 2. All right, so that's just an example of how cosine, it's one specific example of how cosine is an even function. You could do the same thing with sine. You could have sine of negative t is equal to negative sine of t. Or you could have sine of negative theta is equal to negative sine of theta, etc., etc. All the different arguments that we just discussed. If you looked at that one on the unit circle, that's not a very good unit circle. Let's try again. There we go. So if you looked at this one on the unit circle, let's do the same idea. So you have your t. Let's do, I don't know, let's do a different angle. Let's do pi over 4. Start throwing out the very common angles. Pi over 4 is the same as 45 degrees. So the y value here, cosine of t and sine of t, the y value is the sine. So hopefully you remember that. That would be root 2 over 2. I'll write that a little bit bigger. Where should I write that? How about up here? Sine of pi over 4 is radical 2 over 2. If you don't remember that, you're going to have to review chapter 5. And I'll keep bringing these things back as they become necessary. Okay, so this would be the positive angle. Yeah. And then your negative angle would be down here. Negative pi over 4. Just going in the clockwise direction. It's still 45 degrees. Yeah, the reference angle is still 45 degrees. If you memorize the standard triangle, 45, 45, 90. Okay. But since we're going clockwise, the angle is negative pi over 4, or negative 45 degrees. Okay. So notice what happens here. Sine of negative pi over 4, yeah, because you're in quadrant 4, that's negative root 2 over 2. So that's negative root 2 over 2. So this illustrates this property. Sine of negative pi over 4 is negative root 2 over 2. Yeah. And then sine of pi over 4 is just root 2 over 2. These are not equal to each other, but when you bring down the negative sign that's out in front, you just bring it down after you've done the sign. You get negative root 2 over 2 is equal to negative root 2 over 2. So this doesn't prove anything. All this does is verify that this function is, in fact, an odd function, at least for this particular angle. It's true for every angle. I'm not going to sit here and go through every single angle. I'm just going to demonstrate it for one angle, and then you're just going to have to trust me or just understand that it's an odd function. Okay? And if you don't understand, then just trust me. It's odd. Okay? All right, so basically, I only memorized these two. Cosine is even and sine is odd. But you're going to have to know all 6 functions. So you're going to get the others for free. And I intentionally say 4 free because that's how many you're going to get. 4 free. You're going to get 4 free values. All right. Any of the trig functions that involve cosine are all going to be even. So secant is 1 over cosine. So therefore, secant of negative x is 1 over cosine of negative x. But because cosine is even, cosine of negative x is the same as cosine of x. And so this is also even. So this is also even. So if cosine is even, then secant is also even. All right. How about odd? Sine is odd. So any trig function that involves sine should be odd, if it only involves sine. So how about cosecant? Cosecant x is 1 over sine x. So that means cosecant of negative x is 1 over sine of negative x. But sine is even. Sine is odd. I just looked at the word odd and said even. You know what I mean, right? This is odd. So sine negative x, because it's odd, well, that's equal to negative sine of x, because it's odd. So I can just take out the negative, and that's going to be negative cosecant x. So that means cosecant is also odd. All right, so let's make our list here. So we have even, cosine is even, secant is even, sine is odd, so cosecant is also odd. And now what about tangent and cotangent? Well, this one's a little trickier because tangent involves sine and cosine. So which is it? Is it even or is it odd? Yeah. This one's kind of tough because it's a combination of an even and an odd. So who wins? When you make the ratio of an even and an odd, what does the result end up being? You could just guess. I guess it's even. Or you could guess that it's odd. You have a 50-50 chance of guessing right. I'm not going to guess. I'm going to actually do it. So let's see. Tan of negative x. Plug in a negative x and see what happens. You're going to get sine of negative x over cosine of negative x. And then use what you know about sine and cosine. The sine is odd. The cosine is even. So the odd becomes negative sine of x. The cosine just becomes cosine because it's even. Now you can take out the negative. Put the negative out in front. And then do sine over cosine. You're going to get tangent. So it turns out tangent is odd. So when you take the ratio of an odd and an even, you get an odd. So we're going to add tangent to our odd functions. You could probably guess that cotangent, I originally would guess, when I was younger, that it would be even. I would, my original instinct would say you have 3 odds and 3 evens. But my original instinct is not correct. There's actually 4 odds. Cotangent is also odd. For the same reason, cotangent is cosine over sine. Cosine is even. Sine is odd. And so for exactly the same reason that tangent is odd, when you take this negative outside of the sine, it goes out front and you just get negative cotangent. So that completes our list of evens and odds. If you ever forget them, just memorize sine and cosine, and then you can always reproduce the other 4 if you forget them. Okay. So there are 4 odd functions and 2 even functions. 4 and 2. 4 and 2. All right. So now we can simplify some more trigonometric expressions using the even and odd properties. I haven't actually done an example yet today, so let's start with example 1. You know how I like to start over every day. It's like Groundhog Day. Every day starts with example 1. So simplify cosine x minus pi over 2. Right. So keep in mind what we already know. We have our cofunction, which means that cosine of pi over 2 minus x is equal to sine x. That was done in the last lesson. But it must be pi over 2 minus x, not x minus pi over 2. And then you have the even function, cosine of negative x is the same as cosine of x. So keep those two identities in mind while you're working this out. So we have cosine. The first thing we're going to do is rearrange this, negative pi over 2 plus x. Make sure the negative stays with the pi over 2. Then we're going to factor out the negative. Okay. So now we can use the even property. Yeah. Cosine of negative x is the same as cosine of x. So you're sort of thinking of all of this as x. Yeah. So this is negative x. Yeah. And so that means that it's just cosine of x. Sometimes, just for simplicity, we don't use the letter x twice. We sometimes will call this u. You'll be doing that a lot in your calculus course, where you substitute your x's for another variable, like in particular u is a very common one. Okay, so this is cosine pi over 2 minus x, and so that will be sine of x. And that would be your final answer. Example 2, simplify sine of theta minus 90 degrees. Get your identities in mind. So you have sine of 90 minus u is equal to cosine of u. I don't know if that's a very good looking u there. That's your cofunction identity. Yeah, that's why it's called cosine, cofunction sine. And then you also have your odd identity, sine of negative u is equal to negative sine of u. And again, u is a substitute variable. You can use t, you can use x, you can use whatever variable you like. In this problem, I'm using theta. The degrees is implied, so as I'm doing the calculation, I can typically omit the degree when it's clear. So as long as you're sure that that's degrees, you don't need to write it every single time. So this is going to be sine of negative 90 plus theta. So this is going to be sine of negative parentheses 90 minus theta. So again, this is my argument right here, 90 minus theta. And I'm considering that to be u. So this is like sine of negative u, which would be negative sine of u. I wrote that in red because that really doesn't count. I'm just kind of referring back to here in my mind. All right, so I've got, now I'm going to pick it back up. Negative sine of 90 minus u. Oh, sorry, it's not u. It's theta. Although if you wrote u, you could always recover your theta when you're done. And then now negative sign comes down. Use your cofunction identity. The sine of 90 minus theta is the cofunction cosine of theta. Questions? Oh, yeah. I can't hear you. You can ask me later if you have any questions. All right, we're rolling now. Example 3. They're going to get a little trickier now. Simplify cosine of negative x over tangent of negative x plus sine of negative x. Okay. So use everything that we know now. So cosine of negative x. Well, cosine is even. So that's going to stay cosine. It's essentially like the negative just disappears because cosine of a negative is the same as cosine of a positive. Tangent's odd, so the negative comes outside of the tangent. It's kind of like factoring out the negative comes outside. Sine is also odd. Yeah, so it's going to be plus negative sine of x. And you know from basic algebra, we never write plus a negative. We just write negative. Okay. Let's see if I can squeeze in one more line here before I have to work back to the top. So tangent now. Tangent is sine over cosine. I'm going to write it really small and then write it again at the top. I know you probably can't see that. So we're coming back up here. So now we have negative cosine x. I'm just writing it bigger. I'm just zooming in. So I have sine x over cosine x minus sine x. Okay, so now I'm going to flip the denominator. So instead of sine over cosine, it's going to flip and become cosine over sine. Now I'm multiplying two cosines together, so that becomes cosine squared. Remember, we put the exponent after the letter s. It means the same thing as putting big parentheses around it and saying the quantity squared. This is a long one. It might take a third erasure to get through this. Okay, so now we need a common denominator here. Common denominator, so it's sine. Yeah? Sine x and 1, so it's going to be sine x. So we're going to multiply top and bottom by sine x. So now we have negative cosine squared minus sine squared over, now both of these denominators will be the same, so we just say sine x. Now I'm going to factor out a negative sign. You could just put a negative sign, but I like to put -1. Being a little lazy with my parentheses. I guess there's parentheses here, here, and there as well. All right, I'm just going to, instead of erasing again, I'm just going to work up. So that's going to be -1 times 1 over sine x. This is an identity. It's the Pythagorean identity. Pythagorean identity. Cosine squared plus sine squared becomes 1. So this is -1 times 1 over sine. So that's going to be cosecant x. And that's your final answer. Negative cosecant x. Okay, so the last thing we're going to talk about is proving identities. So proving an identity is essentially starting with an equation. The LHS stands for left-hand side, and RHS, obviously, right-hand side. And we cannot assume that this is true. All right, so you cannot, to prove an identity, you cannot prove it by assuming that it's true. That's not the way proving works. You have to start on one of the two sides. It doesn't matter which. You can pick either side. Your choice. Okay. Simplify, working only on one side. You cannot move objects, terms, onto the other side. All right. So everything that you learned in basic algebra about moving things from one side to the other and squaring both sides, you can't square both sides. None of that stuff that you learned in Algebra 1 or Algebra 2, you can't do any of that stuff anymore. All right? And the reason why is because you can't assume that it's true. Right? And so back in basic algebra, we didn't prove things in basic algebra. I gave you an equation. You just assumed that that equation was true, and you started moving things from one side to the other because that's what you're instructed to do. When you're proving something, you cannot assume anything. So you can only work one of the two sides, and then you stop. Stop when one side is exactly the same as the other. Okay? So that's the basic technique for proving an identity. We're going to go from one side, we'll pick one of the two sides, and we'll work it out until it becomes exactly the same as the other side. What are we up to? Number 4? I think we're up to number 4. Prove the identity. Sine t over cosine t minus 1 plus sine t over cosine t plus 1 is equal to negative 2 over tangent t. Okay, example 4. Back to example 4. So we're going to prove this identity. Pick one of the two sides to work with. I usually pick the more complicated side. So that's the left-hand side. You can work only on one side, and then we're going to stop if we can get the left-hand side to exactly equal this right-hand side. Okay. Remember, we can't square both sides. We can't square root. We can't move things from one side to the other. You can't do anything like that. You pretty much only have one trick, and that's multiplying this thing by 1 in some special form. There is a second trick, but it doesn't apply to this example, so I'll save it until it actually matters. One thing that I do just to make the writing a little easier is I omit all the parentheses while I'm actually doing it. And I'm actually going to move over here and try to get as much as I can done, as much as I can fit. So I got sine t over cosine t minus 1, and then sine t over cosine t plus 1. And now I'm going to multiply these expressions by 1, special form of 1. For cosine t minus 1, I'm going to multiply numerator and denominator by cosine t plus 1. That's its trig conjugate, trigonometric conjugate. All right, you want these to have opposite signs. You'll see why when you actually multiply them. When you multiply cosine t plus 1 times cosine t minus 1, the pluses and the minuses will cancel each other out, and you'll get a nice square expression that comes out looking a lot nicer. So let's go ahead and distribute here. We're going to get sine t cosine t plus sine t. That's this first numerator. And then I've got another sine t cosine t, and then minus sine t. That's the second numerator. These denominators are all the same now. So this is going to be cosine t minus 1 times cosine t plus 1. It doesn't matter which order you put it in. These denominators are equivalent. They're the same common denominator, so just write it one time. Now watch what happens when you do the denominator. You're going to go first, outer, inner, last. Yeah, it's probably the whole reason why you took basic algebra, was to learn a trick like that. So let's work on the denominator first. That's going to become cosine squared t. Yeah, cosine times cosine. Remember where we put the square? We call that the shoulder of the function. It's between the s and the t. Then you do cosine times 1. Cosine times 1 is just cosine t. And then you have cosine times negative 1. So that's negative cosine t. Those are going to cancel out. And then you have a negative and a positive. That's going to be a negative 1. So in the future, I will skip this in the future because this will always cancel. So moving forward, I will just jump right to this step where you have cosine squared minus 1. And you can do the same. All right, that's an acceptable pre-calculus level skip that you're allowed to do. Now, I want to point something out. My whiteboard ends right here, okay? So I'm going to move over. It's going to look like I'm working on the right-hand side, but I'm really not. If my whiteboard were to continue down, all of this work is still on the left-hand side, all right? But you're going to have to bear with me. I don't have a big enough whiteboard to keep working down, okay? So again, even though this is still the left-hand side here. All right. Oh, I forgot to do the numerator before I move over here. I've got sine and cosine, sine and cosine, I'm adding those together. So that's 2 sine times cosine. Not squared, but multiplied by 2 because we're adding them together. And then you might have noticed this while I was talking. This is a plus, this is a minus, so those guys are gone. All right. So now we can move over here. We have 2 sine t cosine t all over cosine squared minus 1. Okay, and again, this is actually down here on the lower left-hand side. Okay. All right. Our goal is to get to this. This is our goal. -2 tangent t. All right, looks like we got the 2. Yeah, so we're getting there. Now I want to rearrange the denominator. So this is -1 plus cosine squared t. Just rearranging the order. Very important that when you rearrange a difference, that you keep the difference sign with the term that you moved. So that negative stays with the 1. A very common mistake, I see this a lot in my students' work, is they'll take this and they'll simply rearrange the order, keeping the minus sign in the middle. That's just not true. Okay, so keep that in mind. So now you've got 2 sine t cosine t. We're going to factor out the -1. Yeah, so that negative now factors outside here. And now that plus sign will change to a minus. So now I've got -2. I'm just going to bring the negative up top. Sine t cosine t over, now do you remember, I hope you remember an identity we did in part 1. 1 minus cosine squared is the same as sine squared. That's an identity that you can use from last time, the Pythagorean identity. All right. And then you might also remember this trick. You might also remember this trick where I write the denominator like this. Instead of writing sine squared, I like to write sine sine. Yeah, that's just the way I like to do it. And then I cross off my signs, and it just makes it look more clear what's going on. Okay. The negative can be either with the 2, or you could actually bring the negative all the way out in front like it is over here. We are so close. And so now you have -2 cosine over sine is cotangent. Cotangent is 1 over tangent. And there you go. -2 over tangent t. And I like to put my parentheses back when I'm done. This is now equal to this. And so it has been proven. What I like to do at the end of my proof is I like to put QED. That's the Latin for quo erat demonstratum, or something like that, something in Latin. It means that which I was supposed to demonstrate, or that which was to be demonstrated in Latin. That's, of course, optional. It's just a nice touch that many mathematicians use when they complete a long work. Okay? Or a short work, for that matter. Any proof. Okay, that'll do it for proving identities. That's the basic idea. What I'm going to do next is what we call meet me in the middle. Okay, meet me in the middle. Sometimes you'll find that it's very difficult sometimes we get lost on the way, and you don't make it to the end. And when I say the end, I mean the right-hand side or the left-hand side, or whichever side we're trying to get to. And so this is what's called the meet in the middle technique. Now, this method is typically only used out of desperation. So when you have lost all your way and you don't have any way to go, you do the meet me in the middle technique. You just stop and take a break, and you hope that the other side makes it to where you ended up. So, for example, I want to prove 1 plus cosine over cosine is equal to tan squared over secant minus 1. Okay. So in this example, when you start on one side, you'll start playing around with it, and you'll get to a point that doesn't look anything like the right-hand side, and you might give up. All right. If that happens, what you can do is you can meet in the middle. So that means you work the left-hand side to a particular point, then you stop. Then you move over and work the right-hand side to a particular point, and then you stop. And if those two sides are equal to each other, that is sufficient to prove your case. Okay? So let's go ahead and just work out the left-hand side. All right, so we got 1 plus cos theta over cos theta. All right, so that's going to be 1 over cos theta plus cos theta over cos theta. Yeah. If the denominator only has one term, you can just split your expression into two expressions, and you get secant theta plus 1. So stop here and wait. The left-hand side is done. So this is your, meet me in the middle. All right, I'm not going any further. You got to meet me here. All right. So now you take the right-hand side, and you hope that you can rearrange the right-hand side so that it looks exactly like your left-hand side. And then we will conclude that the two sides are equal. Okay. So we got tangent squared over secant minus 1. So what's tangent squared? Remember your Pythagorean identity, if you remember it. Maybe you don't, right? It was sine squared plus cosine squared equals 1. We divided this by cosine squared. I'm getting kind of sloppy over here. And you get tangent squared plus 1 equals secant squared. All right. It's nice if you already memorize that, but I'm showing you your worst case scenario. If you only remember the sine squared, cosine squared, you can divide it all out and get this one for free. Okay. Then you move the 1 over to the other side, and I get tangent squared equals secant squared minus 1. All right, so this is an identity that you can use. All right, so this is my scratch work here. That's not part of my proof. This is just my scratch work to figure out what I'm going to do with tangent squared. You might just memorize at some point in the next couple weeks that tangent squared is secant squared minus 1. If you do all the homework, you'll probably have it memorized by the end of the homework. So this is going to be secant squared minus 1 over secant minus 1. We're going to factor the numerator. Factor the numerator out. That's going to be secant minus 1 times secant plus 1. That's factoring. Factor the numerator. Bring down your denominator. And now you can cross these off, and you get secant theta plus 1. So these are equal to each other. The left-hand side is now equal to the right-hand side. I never made it all the way. I just stopped halfway, and then I brought down the right-hand side. It stops halfway, and now we're done QED. OK. OK, 7.1 is done. I will get this uploaded as soon as possible. Dr. Jordan signing out.